All right, good afternoon, everybody. I apologize for starting lecture 2 minutes late, right as I was beginning. The entire system here just decided to shut down, so I had to restart it and get it set up. All right, so for those of you who are just coming in, let me go back to the slide. If you could follow the directions at that particular link, that will download the code for what we're going to work through today. So the main idea is we are going to work through the last 5 problems on the midterm exam. And we're going to work through them together, discuss the underlying motivations, and this will allow us to transition into the next unit, which will be basically a lot of graph theory. In graphs, we're going to be building a graph from scratch together. Then we're going to discuss how we would get through a graph, how we can represent a graph in multiple different ways with an adjacency list or adjacency matrix. We're going to code an adjacency list representation, which actually aggregates off of a dynamic array. Then we're going to learn depth first search, which takes advantage of our knowledge of recursion as well as our knowledge of stacks. Then we're going to learn about breadth first search, which is going to take advantage of our knowledge of queues. And then we're going to learn about minimum spanning trees, and we're going to learn about topological sorting. And this will be taking advantage of priority queues, hash tables, and then we're going to learn Dijkstra's algorithm, which is a way of producing the shortest path between 2 nodes in a graph. And then we're going to learn a couple more advanced algorithms. First one's going to be called A*, which is like the foundational search algorithm, which is basically used in Google Maps today. And then we are going to learn about something called backtracking, which will allow us to be able to use recursion in graphs to be able to solve and represent several different problems. So along these lines, I want you to think of today's lecture and what we're going to be doing similarly to a code sprint or a code scrum. So for those of you who, some of you may have had industry jobs, but for most of you, these terms are probably new to you. The idea of a code sprint or a code scrum is you get some sort of task and you have a certain amount of time to complete it. And what ends up happening is the team gets together regularly and performs things, code reviews, and determines how they can improve based on what it is that they have tried on the first iteration. So they go through several times. This didn't work. We didn't understand. Let's put our brains together and work it through. So today we're going to be doing a version of a coding scrum for the midterm. So the first problem is what we call finding the minimum in a rotated sorted array. So this is an interesting problem that addresses several different computational thinking aspects. What you do is you get some sort of array and the elements are initially sorted. And then what's going to happen is the elements are rotated so that the smallest element is no longer on the left-hand side. And your job is to find where that is. So for example, we have 0, 1, 2, 4, 5, 6, 7 here on the left. And then what's going to happen is I rotate it over a few times, and then it becomes 4, 5, 6, 7, 0, 1, 2. So your goal is to find the minimum element. So can anybody first think of any like a brute force approach to how we might solve this problem? What's the simple, naive approach that we'd want to do here? Yes. Absolutely. So what's going to happen is if we iterate through, what we're going to see is that at some point it's either going to be the smallest element or we're going to keep increasing, and then at that point, when it gets smaller, now we've found the smallest element because we know it's sorted. So that's performed in big O of n time. And so here's some examples. Let me go through that. We'd iterate through, and this animation shows precisely what was just proposed by classmates. And so what happens if this expands out and we have hundreds of elements? And I'm going to show you an example a little later where we're actually going to go through about 10,000 and we're going to find it very, very fast. So how can we improve our approach? So what we're going to do is we're going to go through a process that we've actually worked through very briefly in problems where we kind of divide in half and we see what it is that we need to do in order to go back and forth. So when we have 3, 4, and 5, what is it that 3, 4, 5, 1, and 2, what do we actually know? based on any given moment in the array? What are some things that we can claim that we know based on the problem statement? Yes. I'm sorry, we know the size. Very good, that's a crucial point. We know the size, we know there's a beginning and an end. What else can we claim? So how about this? I'm going to stop share, and I'm going to move over, see if this actually works, if I'm going to the correct one. Let me know if I'm going the wrong way. Am I up on the screen? Nope. Yes, I am. Here we go. All right, so we're over here on the whiteboard, right? And wow, I get feedback there. That's wonderful. So we have 3, 4, 5. I'm going to add 6, 7, 0, 1, and 2. So one thing that was pointed out is we know the length. We know that this value, 1, 2, 3, 4, 5, 6, 7, 8, we have 8 elements in this array, right? What are some things that we also know based on the problem statement? Yes. Correct. So we know that at some point we can split this array such that everything to the left is larger than the smallest element, and everything to the right is smallest. So if this actually was 0, 1, 2, 3, 4, and 5, and we didn't sort it at all, this still holds because everything to the left over here and everything to the right, everything to the right and to the left, nothing really changes. Does that make sense? So the crucial thing is we need to be able to figure out some way in which we can determine how to do this. So let me go through and talk about some of the challenges with a divide and conquer approach. So we know the length, right? So we know it's 8. And if we want to figure everything out, what we can pass is 0, and this element is 7. And we want to do 0 and 7 because we don't want to go outside the bounds of the array. Which means that if I want to find the middle, I would do 7 plus 0, 0, 1, 2, 3. So I'm looking at 6. So the crucial thing that we see here is the element at 6, let me say the element at 3, which is the value 6. We have the element to the left is smaller, and the element to the right is smaller. What do we know based on that? What can we prove? Yes. Yes, yes. Either of you may answer. Absolutely right. So the claim is that the smallest value must be somewhere to the right. That is absolutely correct. And the reason we can prove this is because, well, okay, that's smaller, but if this is smaller, that means it has to be over here. Does that make sense? So this is part of what we saw when you were tracing through on the exam. And what we're going to do here in code is we're actually going to code up and see how it is we can make those decisions to go through. So if you are in an interview, I'm not in the screen, so let me move back so that way the students on the Zoom can see. If you're in a job interview, the way you can walk through this kind of problem is first say, all right, there's a brute force approach. I see that I could iterate through and this gets me a big open solution. However, there must be a way to do this. So yeah, when I went through the interview processes, I would actually walk through and state, I know I can prove this, I don't know other things. I even would say things like 0 through 7, I can do that so I avoid going out of bounds. That shows that you understand what's going on in the underlying data structure and that you're thinking about it as you're coming up with your solution. Right, does that make sense so far? Awesome. All right, so what I'm going to do is I'm going to go back up to the laptop and we're going to start actually coding through based on these elements that we have seen. So let me go back and share the screen. So we know all this stuff. What I'm going to do is I'm going to go more to the whiteboard and start explaining stuff like that. And for those of you who really like the animations, I'm going to continue to post them. And we can do one of two things. Either you may read them afterwards, or if there are questions and you don't understand what I'm doing on the whiteboard, I can use the animations as a supplement. Because I know some of you really like those. And I just want to make sure that I'm engaging with the students properly and providing this for reading afterwards. So this is basically everything that we just came up with here. So forgive me for going through fast. All right, so what I would like you to do is I want you to go to source prob1.cpp. And specifically, I want you to go to line 14. That's where our code begins. So in prob1 here, you will see this. This is what's going to show up. So everybody give me a quick thumbs up when you have that. And I apologize for everybody who's at home. I'm going to move the video back over to the normal lecture. Okay, so I'm starting to see a lot of thumbs up. Good deal. So here's what we're going to do. We are going to first say one of the simplest things. We want to come up with a simple case first and then work through otherwise. Well, what happens if we're doing all this and we have our maximum minimum is the same? In this case, we are going to have a template for the function. So we can do integers, we can do long unsigned ints, we can do chars. I'm going to show you examples of where we do strings too. And the reason why I encourage you to do this when you're practicing leap code and things like that is make sure that your algorithmic approaches separate data and structure. A common mistake that is made is that students will get so wrapped up on this idea of trying to make an integer work that they'll wrap up integer and locations in array. So if your solution can template and it works as well, that means you've developed a really good solution. So the first thing we're going to do is like, all right, if max is equal to min, we're just going to return the location of max. And you could do either. You could do max or min. So we find it, we have found the location. The next thing we need to consider is now we're going to start doing the middle. So we're going to say int middle is equal to min plus max minus min divided by 2. So that allows us to be able to do this divide and conquer approach. While you're all typing this out, I'm going to explain the next line of code. I've passed an OF stream to the output. And so what this will allow you to do is when you're practicing, let's say you're practicing for the final and you're trying to do things like this, what you'll be able to do is it will print out to the prob1.txt file the output as we're testing, and you can go back and compare what you think the solution should be to what the solution will be. So that way you can think you can predict the answer and then actually generate your own cases for when you study. So to do this, I just want you to print out, min, max, and mid. So we're just going to say out because, and I see there's a chat. I'll get to that in a moment. We're just going to do min, max, and mid. And then just do endl. We have that here as a pound define directive. So let me check the chat real quick here. Shouldn't line 16 be equals equals? So William is correct. This should be max equals equals min. So we are comparing the two. All right, does anybody have any other questions? Oh, while that's happening, I apologize, the Slack went down. So what we're going to do next after this is we are going to do our 2 main test cases to determine how it is that we can produce. And I see that everybody in the Slack caught my error as well. All right. So I'm trying to balance everything. It's out because it's the OF stream here. It's standard OF stream. So the next thing we're going to do is we're going to come up with these 2 specific cases. And what this allows us to do, and to address one of the questions in the Slack, is by knowing where the mid is, we can actually make these comparisons and perform divide and conquer. And what's going to happen is every time we make a recursive call, these elements are going to print things out. So we can see what the decisions are being made and what's going to be produced on the output. So the mid, we'll say, all right, we can cut this in half and then we'll move in a specific direction. So we're going to first say, well, if the element at the middle is less than, I'm sorry, if the element at the minimum is less than the element at mid, and so the vector is called the vec, and we're going to call dot at min, and this is going to be less than the vec dot at max. We're going to save an intermediary step because I want to do some comparison. So we're going to call this int comp, right? Int comp is equal, and we're going to call find min on out, mid, and max. So if it's less than this way, we're actually going to run recursion the other way. So this will allow us to be able to do these tests and then complete the result here. So int comp is going to be find min, because that's the name of the function. We're going to pass the vec, which we're able to do because it's called by reference, and then out. And then on the left-hand side, we're going to pass the middle, and then the max is going to go the other way. And then once we get this comparison, what we're going to be able to do is we're going to return the comparison between the location at comp and the location at min. And that will allow us to determine, yes. Because, okay, so the question is, why are we going to the left? So this allows us, once we have this way, we can actually, we're going to perform a recursive trace to see if we can make comparisons. And as the recursive trace comes back up, the comparisons will allow us to be able to account for both of these cases. Because we're going to do the same thing to the right. And when you see the recursive trace, the answer to your question will become a little more clear. And I will show that to you when we print everything out. So let me come back to you when we finish the code, and hopefully that will clarify. So now what happens, and the first thing is we're going to say we're going to return, and we're going to perform a comparison here. We're going to say, all right, so if the value at min is less than the value at the comparison, so once we do this, we've performed, if that's the case, we're going to return min, which is the location. Otherwise, we're going to turn comparison. And Gita, to follow up on your question, what this will do is we're able to make these decisions, and then based on these decisions, we'll be able to zero in, and either it's going to be less than this way or less than this way, and it'll come up. So here we have the vex at min is less than the comparison. And once we do that, we return the location of either the minimum or the comparison. The other thing, it's going to be else, and else is just if max is greater than mid, or it's equal. So now we do the same thing. We're going to do the comparison, and we're going to find the mid, except now what we're going to do is we're going to do min and mid. So if it's larger, we're actually going to go in the opposite direction. So this will be min and mid. And then we're actually going to do the same thing. We're going to say, well, if the value at max is less than the value at comparison, we return max. Otherwise, we return the comparison. So it's the identical code. And so if the value at max is less than comp, then we're going to do max and comp here. So this should be min and mid, and then this should be max and comp. And so that's going to be all the coding for problem 1. And so everybody give me a thumbs up when you have that. I will note that they are on the slides. So for those of you who can't attend on time or something comes up, you're welcome to review that so that way you can complete it by this evening. And so what I'm going to do next is I'm going to upload it. And let's see if I did everything right. So you should be able to run make prob 1. If I did everything right, it will run. And I screwed something up because I seg faulted. So here, let me double check. Max and min, correct. Mid is equal to min, max, and minus 2, min, max, mid. If the vec at min is less than the vec at, mid. This is where I seg faulted right here. My apologies. So at my line 23, it should be the comparison of the mid and the mid. Did explain it correctly, but I typed it wrong. So that's going to be where my seg fault occurred. The vec out mid and max. That did that right. Min, comp. Here otherwise, min and mid, max, comp. Okay, so that should fix it. And that will run, and we see that it ran. So when you did get that, I'm going to quickly show this, and I'm going to put the line up that I fixed. If you do vim prob1.text, what you'll see is that I actually have hundreds of elements. So let me show you the code that's produced here. And so the first thing I do is I begin at 12. I have 100,000 values, and I rotate 107 times. And then I iterate through. I print before, I rotate the vec, I print after, and then I print the result of where the location is and what the value is. So I should be able to find where it is, and I hope that I return the value 12. So in Vim, it's going to have all this. I push the arrow key down, it's empty. I push the arrow key down, and now it shows the new rotation that starts at 119. I push it down again, and that shows me all the recursive traces. So this should be able to clarify a little more about what's going on. So I'm performing these comparisons, and we see that that's it. Instead of going through 10,000 elements, I go through 13 recursive calls. And the solution comes out at that at location 9882, we find the minimum is the value of 12. Does anybody have any questions about that before I go on to explaining the character and strings? Yes, I see that there's a hand up. I'm sorry, what? Yes, sure. And while that's going on, what I have here, if you look at your run tests, so I'm going to leave this up here to address the student question. For those of you who have it right, in the function run tests, I have a character array and I have a string array. And it performs that rotation, and we are able to reproduce that. Because we have the template, we are able to separate the data and the structure, and it produces the correct result. So what you'll see in the output is that it will go through, and I believe that the smallest letter is B in the character array. And if you look at, I think it's 4 and aardvark in the string array. So as long as it has the underlying operators that we've worked on in coding challenges before, we can solve this problem with templates. If we have those operators, we could put in our own class and do this. So that means your code is more robust and more useful to other programmers. Right, were you able to get the code? Right, so let me quickly show what's going on here. And if we scroll down, we see that I rotated it. We do 5, and it turns out that at location 5, the value is B. And I have aardvark, beaver, chimpanzee, donkey, elephant, frog, and goat. Rotates, and 3 locations, I find that it is correctly floor and aardvark. Right, so here is the entire code. So let me leave it up for one more second. And I want to describe what's going on with the next problem. So in the next problem, what's going on is we are going to use memoization to solve a problem known as coin combinations. Coin combinations, if I have 11 cents, so first I want to explain for those of you who are not American, weren't born in America, maybe not familiar with American currency, which is very common when I present this kind of problem. I want to point out the American denominations, which will help you break down this problem. So a penny is 1 cent. A nickel, when we say nickel, it's 5 cents. We have 10 cents, and then a quarter is 25 cents. So 10 cents is a dime. So what we can see is there's certain combinations. If I have 13 cents, so if I have 11 cents, how can I arrange that? So the first thing, and were you able to get the code? Awesome. So the next thing I want to show you here is kind of the breakdown of some of the solutions. So you can play with the numbers and min, max, and rotate in here in main, and play with that and see that you can get those results. And then you can play with the code cases as well. So in this problem, showing that it works there as well, apologize. So again, here's the American currency denominations. So for 7 cents, we're going to say that there's 4 possible combinations in this type of problem. I can say that there's 7 pennies. I can say that there is a nickel and 5 pennies. I'm sorry, I can say there's a nickel and 2 pennies, 1 penny, 1 nickel, and 1 penny, or 2 pennies and a nickel. Does that make sense to everybody? So at this point, what you can start to see are combinations. So instead of, okay, the other crucial thing before I go over to the whiteboard is that for 1 to 4 cents, we know that there's only one combination. It can only be 4 pennies. We don't have a 3 cent in this particular case. And then we also know that if I have 18 cents, I can't make anything with a quarter, right? If I have 7 cents, I can't make anything with a dime. And so if I try to say, all right, give me 25 cents from 18, it's not going to work. And so this is going to inform how it is that we actually go through this problem. So we know that -7 here would not be a valid combination. So I'm going to walk through. Okay, so there's several questions in the chat. I'm going to stop share. And now this time, I'm going to go to the chalkboard again. Chalkboard. I'm going to go over to the other one. So this one should be board left, board right. Okay, cool. Students right, not my right. So here is the path for how it is that we're actually going to be able to get through this kind of problem. So if I have 11 cents, here's what I know. Well, let me ask you, how can I break this down if I'm trying to figure out the combinations? If I have 11 cents, what can I first take away from it based on this problem? Any guesses? Yes, I'll go with somebody new, yes. We can take away 10 cents, so we're gonna make that as a combination, right? So we take away 10 cents and that leaves 1. What else can I take away? I'm just going to you because you had your hand up before, yes. You can take away 1, right? So we subtract that and we have 10. What else can we do? Yes. 5, we can take away a nickel. So that brings us to 6. And the other crucial thing that will help you being able to develop base cases is understanding what it is you can't do. So when we draw this out, what we're going to see, if I take away a quarter, that gets me -14. And so now we can see how this ties into potential recursion. We get -14, that means the case is less than 0. That means we don't want to have any solutions. So if I go to 10, now I can repeat this. So at 10, what I can do is I can say 9, I'm taking away a nickel, now it's 5, I take away a dime, it's 0, and see we have now found a combination, penny, dime. So now when we hit 0, we found a valid combination. We get to 9, we can go to 8, 4, a dime is -1, and we can do the same thing with a quarter, that's -15. For space, I'm just going to continue going over here. And we do 7, 3, -2, 6, 2, 5, 1, and 4. So now this allows us to be able to try to figure out what combinations we can get to. We saw a little earlier that anything that's less than 5 is only one combination. It's 4 pennies. So we know that it's 4 pennies here. We also know it's 1 penny here, 2 penny here, 3 pennies here, 4 pennies here, and so on. Does anybody see an optimization for this problem? Yes. Memoization, very good. All right, so what I can do is, as I'm recursing, the way it goes, remember all those animations I had with the stack and the heap? It will call the first recursion. So it's actually going to look like this. It's actually going to go 10, 11, 10, 9, 8, 7, 6, 5, 4, and then it's going to start building the hash. So now what we're going to do is we're going to say, all right, so 4 has one combination. Now I come up here, we have 5. 5 is down to 0. 0 has another one. 5 becomes 4 plus 1. We go up to 6. We have 1 there. If we have 1 here, becomes 1. 6 becomes 2 plus 1, which is 3. 7, we have 2. We still have to put it in the hash, so that's 1. But 7 becomes 6 and 2, which means that we have, I'm sorry, did I properly put that in there? Let me put 6. 6 is 2 and 1, which is 3. 7 is going to be 3 and 1, which is 4. And then we get to 8. We go to 3. We have to hash that. So 4 plus 1 with 8 is going to be 5. We go to 9. 4 is already in our hash, and 8 is already in our hash. So 5 plus 1 is 6. Then we get to 10. 9 is in our hash, and 5 is in our hash. So 10 is going to be 6 plus 2. Then we get to, which is going to be 8. Then we have 6 here. 6 we know is there because it's 3, so it's going to be 8 plus 3. And then we have 1, which is also in the hash. All right, does anybody have any questions about that? Yes. Go over the hash? Okay, so the general idea, so the question is, can you go over the hash again? What I did is I put it in the hash in the order I encountered it. It would be a little different inside an actual unordered map. So what's going to happen here is we are doing the recursion, and the recursion goes like this. The ordering will go 1, 2, 3, 4, 5, 6, down like that. So before we make any other calls, we get here to 4. So 4 is going to be the first element we hash. It's going to be an empty hash, and we want to hash it that way. When we get this, we'll get 4. We know that 4 to 0 is precisely one combination. We get to 0 here, then we move up. 0, we count because 5 minus 5 is 0, so it's a combination. So we hash 0 to 1 as well. Does that make sense so far? Then what's going to happen is, okay, now I'm here. So at 5, I'm going to say, all right, I've made these 2 recursive calls, and with the negative values, I'm going to return 0. So the combination is 4 and 1. We add those together, and we may claim this to be true because for 6 cents, I can either do 1 penny and 1 nickel, or I can do 1 nickel and 1 penny. So that's how I can justify having 2. Then we do the same thing. We go up to 6, and 6 is there. 1 is not in the hash yet, but we have to hash it. I mean, sorry, 1's going to be 1, right? So now this becomes 5 plus 1 gets us 2. We hash it. The value in the key value pair is 2 and 1, and that gets us 3. Right, did that address your question? Awesome. Any other questions? All right, so what I'm going to do is I'm going to go back, check the Slack if there's any other questions, and then we're going to dig into the code. Okay, for a comprehensive solution, would you include func num25 for quarters? That is absolutely, and we're going to do this in the code that we're about to write up. So that is the absolutely thing. So another question, what happens if it gets 2 or more values that are the same? In this particular problem, the way it's phrased in LEET code, that is an assumption that you're allowed to make. So that's from the problem 1. So let me, I'm going to skip over these particular animations and just go straight to the coding. So in the code, what I'd like you to do is I would like you to go to problem 2, and I want you to go down to line 7. And so quickly what we're going to do is we're going to code up this coin combination. And the first thing we're going to say is, well, if, and so here's what it passes. It passes in the unordered map with a call by reference and sense. And let me put this back on lecture so that way those of you at home can see me as well. So we're going to say, well, if sense is less than 0, we're just going to return 0. There's no point in hashing it, no point in wasting memory. It's not going to be a valid part of our solution. Does that make sense so far? The next thing we're going to do is we're going to say, well, if sense, else if sense is less than 5. So we're going to do two things. We're actually going to hash the value to coin map, and then we are going to return that value so we can add it simply. So we're going to say coin map.insert. And the standard template library can accept standard pairs with the bracket foundation. So that's what we're going to use to do it there. And we're going to do sense and the value. So sense is the key, and the value is going to be the number of combinations. And so we're going to put in the value 1. And then we're just going to return 1. And the reason we're going to do that is because at the end, we're going to add everything together. And when we add everything together, what that's going to allow us to do is instead of having to hash, we can just get the return values from this. So that improves a little bit of runtime. So for the next thing, what we're going to do is we're going to save an intermediary result. So let me check to see if anyone's caught any typos. I have not made any, fingers crossed. So otherwise, if we get here, that means we are now going to have some sort. There we go. All right, so now we're going to say int result. And that's going to be equal to what happens when we do a recursive call for 1, 5, 10, and 25. So the first one, we're going to say coin combination. And we're going to pass coin map, sense -1. And then we're going to add to, once you get that, you can copy and paste here and do sense -5. And then if it starts getting long like this, for those of you who are using Notepad++ or Atom, or even in Vim, you can press enter and go down here like this, and it'll still be valid. It's one line of code. Plus, and then you can do -10, and then you can do plus -25. And as everybody pointed out in the Slack, I missed my semicolon, so let me make sure I get it right this time. So to answer the question that was in the Slack, we are now accounting for 1, 5, 10, and 25. So we have two last steps here. So let me explain that while you might be typing up this code. Now that we have the result is the value in the key value pair. The key is the current value of coins. So what we're going to do next is we're going to hash that to the map, and then we're going to return result. So that will allow us to continue to bubble everything up and continue to perform the additions. So we're going to do one last thing. We're going to do coin map.insert, do parentheses, bracket, and then the key is sense, and the value is result. And then the last thing is return result. So some of the benefits of recursion and memoization hand in hand go here. We've reduced the runtime. We don't have to do a big O of n squared to be able to subtract and kind of go back through and kind of loop through and figure out all the possible combinations. And because we're using memoization, we have significantly reduced the number of excessive recursive calls. So recursion can make the coding simpler, and memoization can significantly improve the runtime by saving the intermediary steps. All right, let me check the Slack to see if there's any questions, and then after that, I will compile and run. Okay, I don't see anything at the moment. So I'm going to compile and run to make sure that I did everything right. We'll do make problem 2. And it goes through and it should look like this. If you do vim prob2.text, it will now have all the number of combinations, because I actually run it all the way to 47, and it should show up like this. So I go through, I put in 47, and then I iterate through the end. So let me briefly show you the code that performs this. So inside main, I set num coins is equal to 47, and then I iterate from 0 to iter is equal to num coins, and I call the number of coins has that number of combinations by calling the hash map function. Does anybody have any questions about that particular thought process? Okay, so next thing we're going to do is we're going to move to problem 3. Let me scroll down here a little bit, find it. From coin change 2.10. Okay, so problem 3. Given a string S, find the length of the longest substring without repeating characters. So what's going to happen here is we have a combination of characters, and we want to find the length of the longest substring. So what I'm going to do is I'm going to go back over to the other board. I'm going to write out, and we're going to see if we can come up with some combinations here. And now I'm going to go to board right. So I want to make sure I'm fair to both sides of the class. So I am in desperate need of an eraser. Forgive me. Let's see, board right. This one has an eraser over here, so I'll go back over here for the time being. First time going through this, but working out the kinks. So what's going to happen is we're going to have a set of characters, and this set of characters is going to have some sort of, so if we had an example, so A, B, C, D, E, B, E, and F. So here's what we're going to do. We need to figure out what the length of the longest non-repeating string is. So good rule of thumb, for those of you in my office hours, and I've said this, if it's simple to do with your mind, it's simple to do in code. So what's happened is we can look at this, zoom through it really fast, and we can go, oh, A, B, C, D, E, that's my longest one. So the solution I want is 5. The issue is, if we're going to try to do it this way, we actually have to go back every single time and look things up. So what we want to do is we want to keep track, iterate through in big O of n time, and be able to figure out where the most recent repeat is. So what I can do is I can use dynamic programming. Now, if I wanted to do a brute force big O n squared worst case, I can say, all right, if I were to start here, what would the solution be? Well, I can go A, B, C, and then hit A, and I know the solution is 3. If I go here, I know B, C, A, B. I know my solution is 3. C, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, 4. D, 1, 2, 3. So it ties at 5, 4, 3, 2, and 1. So we see if we analyze it like that, we have that the process I did to do that was big O of n squared. However, we see that if we rack it up like this, that's dynamic programming. So that's a potential solution. All we need to do is keep track of a current value and the location we've recently found the value in the hash and where the most recent repeat was. So if I actually start here, I can start hashing the values into the map. So I can create a map and say 4, and I can say this is 0, 1, 2, 3, 4, 6, 7, 8. So this is going to be 10. And then my current length is going to be 1. I go to E. E is at 9. B is 8. E, we found our first duplicate. So what's going to happen is when I do E, I'm going to say, well, at this point, my current best score is 3. And so that should be 2, yeah. So my current best score is 3 is what I found. And now I have to start here and recount because I have a duplicate. And so I would update the location here, and now the current solution, so a sub-solution, is E and B. That's the last time since I've seen a previous value. So I would need to know the current length, the last place I had a duplicate, and where the values are. So that way I can see whether or not they were there. Since hashing looks up in big O of 1 amortized time, this allows us to reduce that need for keeping track of doing that worst case big O of n squared scenario. So I can walk through it that way, and we can produce our solution and find the result. Does anybody have any questions about that? Okay, so I see one question here. Yes. Sure. So this, when I was coming up with a dynamic solution, the first step I did is, all right, the brute force leads us to be able to figure everything else out here. So brute force big N squared worst case time. What I would need to do is start there and keep track of everything until, sorry about that, to keep track of everything until I find a duplicate. So at the first character is the letter A. So I go, all right, well, I started A, B, C, and then I hit a duplicate here, right? So I know that this, from there until I find a duplicate, is 3. B, C, A, and I hit B again, that means the largest sub-solution is there. And the benefit of dynamic programming and thinking of things as sub-solutions is that if the solution was only this, if I only had that, I would know that my solution's 3. But then I'm adding another character, another character, another character. And what we want to do with recursion and dynamic programming is prevent too much of recalculating. If I already know the solution here, and I can keep track, some way of keeping track of the intermediate steps, why am I doing the work again? Does that make sense? Okay. So I'm going to quickly check the Slack, and then I want to go into the code that will help produce the solution for problem 3. Okay, so Matilda asks, can you explain how you use dynamic programming again? I'm sorry, was that? Yeah, okay, I just answered your question. Okay, so let me go back and share screen. And we have a comment in the chat. When you were starting from the back from problem 3, were you just showing that you can go either way? We are actually going to go from the back and build it up this way, because what we'll be able to do is by starting, let me make sure I'm move the camera here. By starting at the back and moving up, we can actually figure out how it is that we can build up this way. We see the potential solutions, and we can find, by going this way, what it is that will produce results. Let's see, let me move this back here. So I'm going to skip over those slides as well, but they're available. So please go to problem 3 and go to line 15. And so this function is called get longest non-repeat. And so we're going to start at the end and go to the beginning. And so we're going to say int iter is equal to the size minus 1. And because vectors and strings by default return long unsigned int, and you could potentially get overflow, we're actually going to deliberately say as programmers, we understand the risk we're casting. So this is the W conversion. So we have int test string dot size minus 1, and then we have iter is greater than or equal to 0, and then minus iter. So while you all are finishing typing that up, a common question I get is, what's the purpose and benefit of putting it before or after the plus or minus? So when you do that, when you do minus iter, it does it as you start the line of code. If you do iter minus, you do it at the end. For a for loop like this, it doesn't matter because this is its own line of code right here. And it just does everything after everything inside the for loop. So what's going to happen is you can do iter plus, iter minus minus, or minus minus iter. It's convention to do it in front. And often if it's an iter minus minus, but it's inside another line of code, it will decrement and then do the rest. Whereas if you do iter minus minus, it will do everything and then decrement. So what I want you to do next is we're going to update current. And we're going to do plus plus current. And the reason we're doing that is if I encounter a letter, if I say it's 0 and then I say the letter E, well, E right now is the longest by itself. And so to answer Emmy's question from a little earlier, we're going to continue to build up like this until we find a duplicate, and then we're going to repeat ourselves. So let me kind of go through real quick. So the first thing we're going to do is we're going to say if the count, meaning we haven't found the character, is equal to 0. So we're going to do char hash dot count. And this is going to be the specific, the current character. So we're going to do test string dot at iter. And that's going to be the key. And we're going to say if that equals to 0, then we're going to hash it. So we're going to say char hash dot insert. We'll do the same thing with the standard pair. And inside, the key is going to be the character. So it'll be just like this. And then the value is going to be iter. And the reason why it's going to be iter is because that is our current location. So we now know the most recent time we encountered this specific character. Let me add a line here just so it's easier to read. Otherwise, we're now going to get into what we need to do if we find it. So this particular line of code, we're going to say, all right, so if the current value is less than, let's update, hold on, let me check the chat here. I think you meant dot count. Oh, yes, I did do that. So that is count. Thank you for catching that. So we're going to say if current, we're going to say current is equal to, and the first part, this ternary operator will perform a comparison. So we're going to say if the current value is less than char hash, and we're going to use the key of the current location, so that's test string dot at iter, right? And that's now going to say minus iter, like so. If it's less than that, then we're going to say current, and we can do the same thing here. We can do enter and tab to indicate that it's on the same line. Or we're going to have the updated version of this. So it will be the same thing here. So now we've updated the current value. And then we're going to update that hash to the current value. So char hash at text string dot at iter, which is the specific character, is now equal to the new location. And we can do that because it's already in the hash. So we have 2 more lines of code in this particular problem. Outside of the else statement, we now need to check to see if the current value is now larger than the previous maximum. So we're going to do another one of these ternary operators. We're going to say if the maximum is going to be equal to current is greater than maximum. And say, well, if current is greater than maximum, then set the updated value to current. Otherwise, set it to maximum. And then the last thing, I'm going to press enter a couple times so those of you in the front row can see. Scroll here. So this is what we've done in the last few lines. And then the last thing is, at the end, the value is going to be our maximum result. Does anybody have any questions about this? Let me again check the Slack to make sure, address any questions that are there. All right, the first colon on line 26 should be a question mark. So again, thank you for pointing that out. Colin this time caught me. So that should be question mark. If it's true, we have a we need to know what it is we're going to do. What should we going to do? Question mark. Then it's either this or that. And as a side note, while I still see some people typing, for those of you who are in logic design, you're starting to use Verilog, and you see this. Verilog was designed to be based similarly to C++. So if you start seeing these and you're getting confused by Verilog, remember that Verilog was initially designed to take previous HDLs and make them similar to C++, so it would be a little easier for software engineers to be able to program with it. All right, so let's hope that Colin's catch was the only thing that I caught. So it's saying we're going to have another problem 3, and I have all of these different strings that are going to serve as test cases, and then I close the file at the end. So let me run make problem 3. And then you'll see in Vim prob3.txt, these are the sub-solutions and the correct answers based on the inputs. So you have that available to you as well. So let me quickly put this up while I describe what's going on with problem 4. So here's the last little part of what you coded in problem 3. So in problem 4, what that is it was a singly linked list, and you were given some sort of ordering. And this problem is known as alternate the ordering in the singly linked list. So in a coding challenge, you went through and you designed a sorted doubly linked list, right? So in interview type questions, when you're working with linked lists, one thing you have to consider is this idea of the structure. How can you reorder things without moving the locations? So it's one of the reasons why you should understand this type of question, so that way you can demonstrate that you understand how the singly linked list is being implemented on the data heap. So let me quickly go to problem 4 in the slides. I walked through the whole thing here. So if you want to go through and see how we came up with that solution, I have this big animation here that shows how it goes through. So we have, we're at the end here. Problem 4, the problem statement is, given a linked list, reorder it. So we have 0, ln, 1, ln minus 1, L2, L2 minus 2. So the problem statement, given 1, 2, 3, and 4, it should be 1, 4, 2, and 3. And if it's 1, 2, 3, 4, 5, it should be 1, 5, 2, 4, and 3. So that's how they get that specific answer. And so here, let me walk through on an animation here as to what's going on. So if it's for length 4, I'm going to say 4 should go back to 2. Then 1 should go to 4. Then we're at 2, points to 3, and then 3 goes away. If we have 4, what's going to happen? If we have 5 elements, it's going to say 1. If 5 goes to 2, 1's next pointer goes to 5. Then 4's next pointer is going to go to 3. 2's next pointer is then going to go to 4. And then 3's next pointer, because it's going to be the last element, should be null. So let me go back over to the whiteboard again. Your board left. And we'll walk through this step by step to see what it is that we want to do if we have a problem like you had on the exam. So the crucial thing, actually, I'm just going to leave these numbers up because this will emphasize a crucial point. Instead of putting them in order like you might see in the code, what we're going to do is we're going to disassociate the idea of data and structure. So in this particular linked list, I have a set of elements, and they go 3, 4, 5, 6, 7, 0, 1, 2. And so what I want to do is we first, in a singly linked list, if you get a singly linked list interview type question, first thing you should think, recursion. And the reason why is because in a singly linked list, you know the next element, but you don't know how you got there. So the first thing we need to do is we need to go, all right, I need to figure out where the end of this list is. If I'm going to do this, I first need to go, all right, right? But the other crucial thing is you only know the next element. And we need to figure out a way to understand where we began. So we also need to pass the head every single time. So once we get here, this allows us to say, all right, I know where it ends, and I also know head next. Does everybody see that? So once you see that you know head next and you know where the end is, now you can start going through the process of linking them together. So before, I can say, all right, where I've recursed, this is null. Not anymore. I know where head next is. And with head next, I want to alternate. So I want to start at the beginning. So I'm actually going to say, nope, I'm going to get rid of that. And I'm going to point here. So now we have 3 and 2. And now we're here. So what's going to happen is when I'm done, if I recurse back up, I can actually move these. And so now I can go through the same process. I can say, all right, I'm going to do 1 to 5 because I know where 4's next is. And then I can say, well, 4 is going to go to 1. Do the same thing with recursion. Do 0 and 5. I know where 5's next is. That's 6. 5 is now going to point to 0. I do recursion again. And right now, we see that when they're different by 1, 6 is already pointing to 7. So this works out. 5, 6, yeah. So if it's an even, we're going to run into a different problem, which is that if it's even, let's say I got rid of 7, right? At this point, 6 is pointing to 0. So what I'm going to do is I would just set that last value to null. And then we have our valid solution. This becomes 3, 2, 4, 1. That's right, it should get about 4, 1, 5, 0, and 6. So now we have the alternating values. So this was good because now we can see how the linked list works on the, we understand that we can demonstrate how it's working on the heap, and we don't have to worry about understanding where the data is because we want the data to stay put anyway. So it doesn't even matter. We shouldn't even be thinking about how that works. So let me quickly go through and do problem 4 in code. Does anybody have any questions about that before I continue? All right. Let me quickly check the Slack to make sure. I don't see anything in the Slack. I do see something in the chat. Okay, so you caught the same error I made last time. So let me share my screen. I'm going to get out of the slide here. And then what I'm going to do is I want you to go to singly linked list, and I want you to go to this method reorder list. And that is at line 23 at include singly linked list. And so this is going to be recursive. And first we're going to say that I want to keep track if I found the end of the list. So I'm going to say bool reached end is equal to false. And then what I'm going to say next is that if end of list, so here I have a node that I am passing by value. Yes, pass by value. And then I am calling the beginning of list by reference. The end of the list I'm not going to change, but the beginning of the list, I'm going to manipulate that. So if I've reached the end, it's false. If I say the end of list, if that's next value is not null, then we're going to make another recursive call. We're going to say reached end is equal to reorder list, and that's going to say end of list next, because that's going to be my next end of list, and then I'm going to keep track of the beginning of the list each time. So that allows me to figure out where the end of the linked list is. If I got here, we've made all the recursive calls, and we said reached end is false still. Then we're going to start creating temporary nodes to be able to perform our changes. So what we're going to do is we're going to say we're going to create a node. So in this case, in the singly linked list, we have node T star, so it's just a pointer. It is very much like a void pointer, except the node class gives it context and the template gives it context. But it's not an actual node, it is pointing to a location on the data heap. And we're going to call this begin next, and this is going to be equal to begin list arrow next. And the reason I'm doing this is just in part to make the code simpler to read and understand. And now I'm going to create another node pointer, and I'm going to call it temp end. And we're going to call this end of list. So we're going to make two decisions. And so what I want to say before here, just for simplicity, because we were running a little low on time, if I want to say else, we're going to say return true. And that allows us, once we get to the end, to just be done with everything. So now we're going to do two decision statements. The first decision statement is if temp end is equal to the beginning of the list, so we have the two lists pointing at the same location. So this counts for what happens when we reach the same place. Remember that one case I showed you where it's even is actually up on the whiteboard for those of you who can see. So for those of you on your board left, so on the board, it's zooming in. Remember I made it even, I have to disassociate the tail. And we have that same case if temp end equals begin list next. And in this case, we actually have to set the temp end next to null. And then once we do that, we can say that we return true. The else case, as you're typing, I'm going to finish explaining it. The else case is when we did this other main step on the whiteboard, where we went back and forth several times. So now we're going to update the temp ends next pointer to begin next. Oh, I'm sorry, I saw there was the chat has disappeared on me. Is that it? It is. All right, line 30, I think you forgot the T, I think. Thank you, Marcelo. At line 30, node begin next. Very good, thank you. So in this else case, this is where we actually do the non-terminal case. And we're going to say temp end next. And that's the case where if you see it on the whiteboard, it was initially 3, and now it's pointing to 4. So we have to point to begin next. And then begin list next. That's going to be equal to temp end. So now that gives us this circular pattern. The last thing we're going to do is we're going to update this begin list because we've called it by reference. So now when we curse up, we actually set it to the next value so that way we can get them to go towards the middle. So we're going to set begin list is equal to begin next. And then we're going to return false because we have not reached the end of our algorithm. Okay, so while you're all doing that, I'm going to check. Okay, so begin next on line 30. Natalie caught my same mistake. Thank you all for that. Does anybody have any other questions? All right, so I'm going to update it, and we are now going to see that this code will work. All right, comment in the chat. If I'm able to see it, let me check. Here, single equals on line 35. Thank you. Line 35, yes, equals null. Okay, so I'm going to update that and compile it, and we'll do make prob4, and we see that it works. And if we do vim prob4.text, what we have in the main function is several different lists. I print the first 3 out. I do 2 with integers, and then I have wake the cheering name her echoes up. And if we work it out, we see that's 4, 1, 4, 2, 3, the answer that you got on the problem in the exam, and then the correct ordering, wake up the echoes cheering her name. Okay, thank you all for catching that on those little typos. All right, so let me put up the code, and I'm going to explain the last problem. And the code in the last problem is on the slides. So I'm going to, if you would be so kind and go through and work on that on your own and complete problem 5. But what I'm going to do is I'm going to set up the motivation for problem 5. And then I will also point out that after the lecture, I clone and up the link that says the lecture link, it will actually have the solution. So you can go through and check that to make sure that your code is working. But I would encourage you to continue to work through it in class. So those of you who are asking those questions, I like those questions as a good discussion. I hope to continue that. So the motivation for the last problem, I'm going to go to your right, is something called a graph. So in graphs, how this works is we are going to say, I have a node, and in the node, I can point to several different nodes. And these nodes can point to each other. I could have another node here, another node like so. So this can get pretty complex if we try to do it like we're doing with a doubly linked list or singly linked list. So if I put in the values 0, 1, 2, 3, 4, and 5, I can represent in the graph what's known as an edge. And the edge is what you saw in the standard vector of pairs. So in the standard vector of pairs, 0, 1, we have 0, 2, 1, 2, 1, 3, 1, 4, and 2, 4, and 3, 5. So actually, since it's just hit 2 o'clock, what I'm going to do is work on problems 1 through 4 tonight. We'll start with problem 5 in this lecture to begin next lecture because it ties in with what we're going to be learning, which is depth first search. I want to very quickly go over the idea here, and then you're dismissed. So what's going to happen is I have to choose a path to go. So in a depth first search, I'm like, well, I encounter 0, 1 before I encounter 0, 2, so I'll go this way. Then I'm here, and I'm going to go, well, 1, 2 before 1, 3, I go this way. And if I'm trying to find 5, I would go to 2 to 4. There's no outgoing. And the way I can keep track of all of that is by using a stack. And that's what we did in the problem. So we can go back. We go here, and then we try the other path. We then say 1, 3, and 3, 5. And then when we go backwards, we would actually use the stack to say, all right, 3, 5, 1, 3, 0, 1. And then what I had you do at the beginning, we'll go into more detail, is I had you put in another element, -1, 0. This indicates that it terminates. And then when you printed out the last elements, it printed out 0, 1, 3, and 5. So please continue, finish up problems 1 through 4. Please ask questions on the Slack. Problem 5 will be done first thing. And when we do that, I will have the TAs go through and upload your work. I want to hit the last slide, because the last 2 slides, because that's important about how these will count. So go back to lecture and share screen, share. I'm going to go all the way here, and then I'll dismiss. All right, so the way this is going to work, wow, that's really small, from current slide. So these problems will count 100 out of 100 towards your midterm score. So if you had a 410 out of 500, which was the median, it will become 510 out of 600. And so that will add a few points to your average. And so The one thing I want to point out, and this is the last thing and then I'll let you go. So please do not consider this a curve. I don't like the term curve because curve implies that you didn't earn it. I'm just giving you, I'm a beneficiary, I'm very kind, I'm a benevolent dictator, I'm giving you points. That's not what's going on here. You are working extremely hard in this class, systems programming. For those of you who have logic design, second semester, sophomore year can be pretty tough. And based on some of the feedback, for those of you who saw my email, I've come up with better ways to ensure that the exam is in a good time frame. I thought it was going to be good. It was a little over, it was longer than I thought. I apologize for that. Doing the mock exam, I hope will be able to get everybody on the same page in terms of my expectations and student reality. So I call this instead a reward for willingness to be challenged. You're in this major, you picked a hard one, but you're going through it, you're doing the work, and I congratulate you for that. You did well on the exam anyway. I know some of you feel frustrated, but you still did well on the exam. You've earned this. So we're going to continue doing this work, and I will see you all next week.